Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So from the introduction about the properties of light, we learned that light is absorbed and emitted in discrete units called quanta or photons. So now we want to talk about the photoelectric effect. And basically, light ray is a stream of electromagnetic energy made up of photons. And here, something that we need to take into consideration is that intensity of light, that is proportional to the number of photons. And then the energy per photon is given right here as h nu. And so h is Planck's constant. And basically it's a value of 6.63 times 10 to the power of negative 34 joule second. Joule is a unit of energy, second is a unit of time. And frequency is in the unit of second to the power of negative 1, giving us a unit of joules for the energy. So, basically the photoelectric effect is the observation that many metals emit electrons when light shines upon them. So incident photons come in, and then electrons are emitted from the metal, and these ejected electrons are called photoelectrons. And so according to classical electromagnetic theory that we talked about before, this effect can be attributed to the transfer of energy from light to the electron in the metal. From this perspective, an alteration in either the amplitude or wavelength of light can induce changes in the rate of emission of electrons. Furthermore, according to this theory, a sufficiently dim light would also be expected to have a lag time in the initial shining of emitting an electron. Basically, if you have a dim light, you are less likely to eject electrons quickly because it takes some time for it to hit the electrons and allow them to be kicked off. However, it actually turns out the electrons are only dislodged by the photoelectric effect if the light reaches or exceeds a threshold frequency. This is the critical part, below which no electrons can be emitted from the metal, regardless of the amplitude or the length of exposure of light. So basically, if you look at this, when you're at 700 nanometers versus 550 nanometers versus 400 nanometers, you can see that the max velocity of the electrons that are being ejected can be changed. However, at 700 nanometers and at 1.77 electron volts, you actually see no electrons being ejected. So basically, this is telling us the work function, or the threshold, which I'm going to write down right here, work function, and this is given this sign, and this is the threshold that an experiment needs to obtain in order to eject a photoelectron. So basically, Albert Einstein, the guy that I'm sure you guys have all heard of, proposed that a beam of light is not a wave propagating through space, but rather a collection of discrete wave packets or photons, each with an energy of h nu, as shown right here. Okay, so now from here, we can create this equation, where the energy of the photon minus the energy required to remove an electron gives you the excess energy, which in turn can be written as Ek, which is the kinetic energy of the electron, basically the kinetic energy of the electron that's being ejected out of the metal. Now we can rewrite this as the energy of the photon, E equals h nu, seen up here, minus the work function, which is the threshold, right, that we talked about before. And in this particular example, it says potassium needs negative 2.0 electron volts to eject an electron, so that's actually the threshold energy required. And that can also be rewritten as half me, this is the mass of the electron, ve, which is the velocity of the electron squared. So in classical mechanics, we know that kinetic energy is 1/2 mv squared, right? This is the exact same equation, except we're talking about the kinetic energy of an ejected electron. So unless the energy of the photon is greater or equal to the energy required to remove an electron, then an electron is not emitted even for high intensity light. So what that means is if you don't reach that particular threshold, we're not going to get ejected electrons. So if light only had wave properties, then increasing the intensity of the light should end up in ejecting more electrons. So from here, we can actually do a lot of different worked examples, and using the photoelectric effect, we can calculate different wavelengths, different frequencies of light, and I'll show you those problems right now.